All right, let's jump right into this explainer covering Module I. We're going to be unpacking the fundamental rules that govern the physical world around us. If you've ever just stopped to marvel at how massive steel ships manage to float, how airplanes actually stay up in the sky, or hey, even how water perfectly flows out of your kitchen tap, well, you're already observing the exact principles we're about to decode. So welcome to our deep dive into the foundational architecture of fluid mechanics.
But before we get bogged down in the rigorous applied science and all those mathematical equations, we really have to ask ourselves a basic yet incredibly profound question. What fundamentally drives the behavior of every single fluid we interact with? Because a fluid isn't just a liquid like water, right? It's also the air we breathe. Literally, it's any substance that continuously deforms under applied shear stress. But why does a jar of honey pour so slowly while a glass of water splashes in an instant? Or why does the pressure build up so intensely the deeper you dive into a pool? These aren't just random flukes of nature. They are governed by strict, totally predictable, and measurable laws.
And this lays out our exact roadmap. It's a comprehensive 5-hour syllabus mapping out Module I to hit course outcomes CO1. We're looking at a master plan divided pretty cleanly into two main buckets: properties of fluid and fluid statics. It's concise, it's packed with crucial concepts, and over the next few minutes, we're going to break down exactly what this 5-hour academic journey is going to look like. So, we'll be tackling this in 5 distinct steps. First, the significance of fluid mechanics. Second, core properties and viscosity. Third, categorizing types of fluids. Fourth, fluid statics and core laws. And finally, hydrostatic forces on surfaces. Let's get to it.
Section 1. The significance of fluid mechanics.
We kick things off in Section 1.1 by really establishing the absolute necessity of fluid mechanics in the applied sciences. I mean, why spend 5 hours studying this? Wow. Because fluid mechanics is literally the bedrock of modern engineering and physics. Without a solid grip on these principles, doing things like designing cardiovascular medical devices, predicting major weather patterns, optimizing aerodynamic cars, or even just building municipal water networks, it would be entirely impossible. The coursework starts here to ground your learning in real-world stakes. Because honestly, before you start crunching numbers, you absolutely have to understand the why.
Moving on to Section 2. Core properties and viscosity.
Within this module, you'll discover the specific properties of fluid that give every distinct liquid and gas its unique, measurable characteristics. Think of this as the actual DNA of a fluid. We're talking about attributes like density, how tightly packed the matter is, alongside specific weight, specific volume, and specific gravity. You simply can't predict how a fluid will behave inside an engine block or a complex pipe network until you know its fundamental makeup. This section makes sure you can mathematically describe the physical reality of whatever substance you're looking at.
Now, a huge piece of this puzzle is Newton's law of viscosity. This mathematically dictates how these fluids resist flowing and shifting around. And this is arguably the most critical dynamic property you're going to study in Section 1.1. Viscosity is, essentially, fluid friction. It's the whole reason motor oil protects your car's engine completely differently than water would. Newton's law gives us the actual equation to measure that internal resistance. By understanding that shear stress is proportional to the rate of shear strain, you unlock the ability to engineer systems that require lubrication, you can predict pipeline drag, and you can fundamentally control how a fluid moves.
Which leads us right into Section 3, categorizing types of fluids.
We're going to wrap up our focus on dynamic properties by learning how to correctly identify and categorize the different types of fluids out there. Because let's be real, not all fluids play by Newton's rules. Is it an ideal fluid with zero viscosity? Is it a real fluid? Maybe it's a standard Newtonian fluid like water and air. Or maybe it's a non-Newtonian fluid. Think blood, toothpaste, or even quicksand, where the viscosity actually changes under pressure. Knowing exactly what type of fluid you're dealing with dictates which mathematical models you're actually allowed to use moving forward.
Okay, here is where we hit a really dramatic pivot in the module. Once we understand how a fluid behaves dynamically under Newton's law, we completely shift gears. We freeze it in place to study fluid statics. Section 1.1 was all about the intrinsic properties and the potential for flow, right? But in Section 1.2, we take velocity out of the equation entirely. We aren't looking at fluids in motion anymore. We're looking at fluids at absolute rest, and we're analyzing the tremendous, invisible, pressure-driven reality that exists within that stillness.
Section 4. Fluid statics and core laws.
First up in this stationary domain is a heavy hitter, Pascal's law. This is an absolute rule of the universe.
Pascal's law states that a pressure change at any point in a confined, incompressible fluid is transmitted throughout the fluid such that the exact same change occurs everywhere. It's wild when you think about it. This single principle is the magic behind hydraulic lifts, your car brakes, and massive construction machinery. By mastering this, you're learning how a tiny input of force can be multiplied to lift literally thousands of pounds, simply by understanding how a fluid behaves at rest.
Right on the heels of that is the hydrostatic law, which builds on that stillness to help us understand how these elements behave under their own weight. Have your ears ever popped when you swam to the bottom of a deep pool? Well, that is the hydrostatic law in action. It tells us that the rate of increase of pressure in a vertically downward direction must be equal to the specific weight of the fluid at that point. In plain English, as you go deeper, the pressure goes up linearly because you literally have to support the weight of all the fluids stacked above you. It's an incredibly elegant equation, and it's vital for everything we tackle next.
And finally, Section 5, Hydrostatic Forces on Surfaces.
Watch how this module boldly dials up the geometric complexity. We're going to start calculating hydrostatic forces on surfaces, starting simple with horizontal, then moving to vertical, then inclined, and finally culminating with complex curved geometries. I mean, just picture a massive concrete dam holding back a reservoir. The water is totally stationary, that's fluid statics, but it is exerting millions of tons of force. In this final stretch of the 5 hours, you're going to learn how to calculate the exact force and the center of pressure on a flat horizontal bottom, a flat vertical wall, a slanted inclined gate, and finally those complex curved surfaces you'd find on submarine hulls or arched dam walls.
So after completely unpacking the intrinsic properties of matter, figuring out how fluids resist flow, locking down the universal rules of pressure, and calculating immense forces against curved underwater structures, what does this all mean for you? After you wrap up these 5 hours of foundational Module I coursework and really nail down Course Outcome 1, what real-world engineering challenges are you going to solve next? Will you be the one designing the next generation of deep-sea submersibles? Or maybe a revolutionary new hydraulic mechanism? The foundation is set, but the applications, they are infinite. Keep exploring, keep asking those big questions, and I'll catch you in our next explainer.